Hi everybody, I hope this video finds you well. Today we're going to be continuing on talking about the least squares regression line that we introduced in the last video. We're going to talk a little bit about some of the features of this LSR and then do an example where we once again sort of go through the process of building the LSR and understanding how it really models the data that we're looking at. Before we get to that though, let's talk a little bit more about the components of the least squares regression line. So remember that the LSR is a linear model, and the common way to sort of write that linear model, as you guys learned in algebra classes, is in that slope-intercept form. So we're usually writing it like this, ax plus b. Now you will notice that we're using a little bit of different notation just to be a little more careful here. On this left-hand side, we're writing y with this little caret or hat on it. All that means there is this indicates that these are predicted values, right? And that sort of hints at what the linear model is really there for, right? It's supposed to sort of predict values of the response based on values of the explanatory. Now, as we talked about in the last video, this is a totally fine way to write it, but do keep in mind, you can also think about this as the response variable as a times the explanatory variable plus b, right? This over here is the more algebraic notation. This is more the one that we want to sort of think about because this y represents that response and this x represents that explanatory. So let's talk about some of the components of this stuff. So first of all, this value a here, right? So we know that a is the slope. That's the sort of name for that piece of the linear model. So what is the slope? Well, just remember, slope tells us what happens to y when we increase 1 unit of x. So what the slope actually is there for is to tell us basically as we increase by a single unit of whatever x is, that value, the slope, tells us what happens to y. You guys probably remember that from seeing like in algebra classes, like that concept of rise over run. This is just saying that sort of in words here. All right, the other component that we want to talk about, let's just switch colors here. That looks good. All right, so the other one we'll talk about right here is this guy. And that value b is what we call the intercept. Now, if you remember, again, from algebra, the intercept is what happens when x is 0. And you should be able to sort of see that. If x was 0 in this model right there, that term would drop out, and we'd be just left with y equals b. So the intercept tells us when x is 0, the intercept is the value of y. And you can sort of start to think about this as sort of a starting point, right? This is sort of like the starting point of the model. Now, as we sort of do more examples, like the one we're about to do and in later videos, we're going to see that the slope is always something that we're going to want to sort of talk about or interpret because it's always going to make sense in the context of whatever we're studying. The intercept is important, but sometimes it doesn't make a lot of sense. And the reason that that intercept is sometimes not going to make sense is that it comes along with this assumption that x is 0, which is basically saying that the explanatory value is 0. Now, some variables can be 0, in which case the intercept is going to make sense. But other variables out there won't really ever, in real life, take on a value of 0. So the intercept in those situations will sort of be nonsensical. So we'll get used to that as we do more and more sort of examples of this. All right, the last sort of note that we want to sort of make here, and we sort of already indicated it here with this little bit of notation here about this sort of hat notation on the y, is that the main use of the LSR is to make predictions. And what that basically is saying is that once we've sort of built this linear model here, What we use it for is to say, okay, what if we didn't observe every possible value of the explanatory? We can still use this model to predict what will happen with the response variable based on different values of the explanatory. And we're going to study this idea of making predictions a lot more in sort of future videos, but we'll even do a basic example of it in our next example. All right, so now that we've talked about slope and intercept and this idea of making predictions, we're going to go ahead and take a look at our next example here. All right, so this example here says that we want to suppose that we have a food truck owner who wants to study the relationship between the number of customers that they get each day and their daily profit. So what they do is they go through and they record both of these variables for 9 days and get the following data. So on one of the days, they had 22 customers and made a profit of $50. One of the days, they had 18 customers and made a profit of $60. And this day, they had 36 customers and made a profit of $120. So you'll notice that the list of things that we're doing with this is growing sort of steadily. Initially, we just knew how to build a scatter plot. Then we learned how to do the correlation coefficient. Then we learned in the last video how to write down the LSR and graph the LSR. And now we've got a couple more components in E and F about the slope and the intercept, as well as making a prediction. So this example will run us through all of those pieces here. Once again, I highly recommend going through, before we move on to the next piece here, putting this data into your calculator and following along as we do that. Of course, before we can put it into our calculator, we do need to remember one very important thing, which is which variable is going to be treated as explanatory and which is going to be response. Obviously here, if we're trying to determine if there's a relationship here, it would make sense to say that the number of customers might help explain the profit that we make. So in this case, this will be our explanatory variable, and we'll want to put that in L1, and this will be our response, and we'll want to put that in L2. All right, I'd go ahead and get this data sort of typed in, and then we'll move on into our next page to actually have enough room to sort of work through the different pieces here. All right, so let's do that. There's our data there, and we've got a couple pieces that we wanted to do. Let's go ahead and first start with that scatter plot. So for the scatter plot, we'll give ourselves our sort of nice little coordinate axes here, and we got to sort of think about how we want to label these. So our explanatory variable, that's going to be the number of customers. All right, for number of customers, looks like the lowest was 18, and the highest was that 57. So we just got to pick a nice easy scale there. I'll just pick sort of round numbers. Let's go 15, 20, 25, 30, 35, 40, 45, 50. Looks like I'll need to extend that a little bit. 55 and 60, right, to make sure that we can see all that. Now for our profit, it looked like the low profit was at 45 and the high profit was all the way up here at 200. So we'll need sort of wider axis there, just out of convenience. Yeah, I don't know, let's just go ahead and actually, we'll just label by sort of larger values. Let's just go 50, 100, 150, and 200. And of course that's daily profit there in dollars. And once again, we should probably put a little squiggly line in here indicating that that little section of 0 to 15 in terms of the customers has been sort of condensed into that portion. We don't need anything here though, because our scale is by 50s, and this section here is a standard 50 units. All right, so let's go ahead and quickly plot this stuff. We had 22 customers in 50, so we have a point like right about there. We had 33 customers in 125, so that looks like it should be right about there. Then 29 customers in 45, so that should be maybe right about there. 46 customers in 165, so that should be somewhere maybe right up about there. 18 customers and 60, so that should be maybe somewhere right about there. 57 customers and a profit of 200, so somewhere up there. 47 customers and a profit of, what was that, 135. So that should be maybe right about there. 42 customers and a profit of 150. So that should be right about there. And then finally 36 customers and a profit of 120. So somewhere maybe right about there. All right, so there we go. There's our scatter plot there. Now again, before we even go to calculate the correlation coefficient, we can think about what sort of general sort of thing that we're seeing here. Obviously, it doesn't make any sense to sort of view the data like that. Instead, we're sort of seeing a positive relationship, something like that. So we're expecting an R value that is going to be positive with this data. All right, let's go ahead and calculate that R value. So for B, we'll go ahead and get our R value. Remember that to calculate this R value, you'll want to pop this data into your calculator and use that linreg AX plus B. I believe I already have mine in, so this shouldn't take too long. If we go ahead and do that calculation, that linreg AX plus V, we'll just go ahead and get that. And it looks like we should get an R value of 0.9244. And you guys will notice that this is, as predicted, a positive value. Is it a strong enough value to count as a true relationship? Well, it does seem pretty close to 1, but we can confirm that by using our sort of table E. So let's look up on table E. We can go back and quickly count 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. So we know we have n equals 9. That's going to tell us, we'll just quickly pull up table E. There we go. We've got n equals 9 there. We've got 0.025, so we're right there at 0.6664. So that's our critical value. Let's go back and write that down. The critical value here is 0.6664. Now again, the absolute value isn't necessary here because this is positive, but we're just going to write it anyway to remind ourselves. We can check that the absolute value of R, that is indeed greater than the critical value. So this tells us that there is enough evidence for a positive correlation. So in other words, this pattern that we're seeing here really is a strong enough pattern to believe that the number of customers you're getting really does tell us about that daily profit that you'll be making that day. All right, the next thing we wanted to do was get that LSR. Remember, that's also going to just be directly from your calculator. You can record the A and B here. The A from the calculator looks to be about 3.98. We're going to keep a couple decimal places because it's pretty small. And the B is negative 29.34. So that tells us that our LSR, the actual equation, is y with that little hat, 3.98x minus 29.34. And of course, it is essential that if one of these values is negative, you make sure you include that negative there. This form that I wrote the LSR in right there, that's a totally fine form to use. However, it does hide what the variables were. So let's just go ahead and rewrite it in terms of the actual variables. So the y is the daily profit here. So we can say that the profit, or more precisely, the predicted profit, is 3.98 times the number of customers minus 29.34. So here we're just filling in that x is the same as the number of customers and y is the same as the profit. So there's our LSR. Now we did want to go ahead and draw LSR on a scatter plot. So we will need 2 values again. So need 2 points. Again, you can choose any x values that you sort of like. So you can choose somewhere at the low end like 15 or 20 and somewhere at the high end like 55 and 60 and see what values you get there. So let's just go ahead and use x equals 15. Right, and then we will get that our predicted y value is 3.98 times 15 minus 29.34. Typing that into your calculator, you get 3.98 times 15 minus 29.34. And you should get, once you do that, if you type it in correctly, you should get 30.36. So we'll make a little note here. Our first point is going to be 15, comma 30.36. Let's do the second one real quick. We'll use x equals 60. We'll get y hat is 3.98 times 60 minus 29.34. Typing that in, we should get 209.46. So we'll record that value as well, 60, comma 209.46. Let's go ahead and draw those on. 15 and 30.36 should be somewhere right about there. And then 60 and 209.46 looks like we should have somewhere right about there. And if we attempt to sort of sketch those in here, connecting those two dots, there we go. All right, so again, notice that when we do that, right, when we actually sketch in that LSR, it does generally go through the points here, right? It sort of cuts approximately through the pattern of our data. All right, now, of course, if you wanted to, you could choose different x values to plug in. You could have plugged in like 20 and gotten there, and maybe 55 and gotten there, and then draw the same line connecting it. Doesn't matter what two x values you choose, you just need to pick two that are going to make it easy to draw it on the scatter plot. All right, now we're going to move into some newer things. The first thing that's sort of newer that we're going to talk about is we're actually going to try to interpret that slope and that intercept. So let's go ahead and do that. So let's talk about the slope and the intercept. Well, to do that, we need to identify the correct values. So for the slope, we know that the slope is that first value in our LSR. So it's that 3.98, the first component. Now we said that sort of algebraically, slope means that when you go up 1 in x, this slope value is what happens to y. So that means we will go up 3.98 in y. How do I know that we're going to be going up 3.98 in y? Well, it's because this is a positive value. If this slope was negative, then this would be going down by that amount. All right, this is a fine interpretation in terms of algebra, but we need to say a little bit more for our situation. So what does it mean to go up 1 in x? Well, x, of course, was the number of customers. So that means when we go up 1 customer, well, what is y here? Well, we know y is the daily profit. So we go up 3.98 profit. Now we just want to attempt to say all that, right? This up 1 customer, up 3.98 in profit in terms of words. So we would say our model predicts that for each additional customer, not customers, customer, we will increase our profit by $3.98. So notice that when we go to write this interpretation here, it's basically a chance for us to talk about this sort of units and put it in context with the variables that we're studying. So we're saying that according to the data that we see here, each additional customer who shows up increases our profit by about $3.98. All right, let's go ahead and talk about the intercept. The intercept here was the other value, right? It's the other one that we sort of wrote down. It's that b value that we wrote here, or it's that negative 29.34 that we put there. So it would be negative 29.34. Remember, algebraically, the intercept is that when x is 0, y is supposed to be whatever that intercept is. So in this case, y would be negative 29.34. Well, what does it mean for x to be 0? That means that when the customers equal 0, the profit is negative 29.34. Okay, now that sounds a little bit weird. How can profit be negative? But then again, we can think about that profit and being a negative is probably a loss, which makes sense if nobody shows up. So what we're saying is our model predicts that when 0 customers show up, we will lose $29.34. And if you think about that in sort of a business sense, this $29.34 is apparently the sort of operating costs that we would have that even if nobody shows up, that we're going to lose. Now that could be maybe paying people or paying for the equipment or the supplies or whatever. But apparently if nobody shows up, according to our data, we're going to lose about $29.34. All right. So you'll sort of notice that these two things together tell us how this model works. If 0 customers show up, we expect to lose $29.34. Then, for each additional customer who does show up, we gain $3.98. Eventually, if enough customers show up, then we'll start to make money because each one is increasing the profit by about $4, and eventually we'll overcome that initial overhead we have and begin to actually make money. All right, we had one last thing that we wanted to try to do with this, right? We wanted to go ahead and predict the profit when you have 40 customers. Well, this is going to be one of the most common applications of the sort of LSR. Whenever you guys see a mention of predicting, what that is going to mean is that you're going to be plugging in to your model. Now we know the number of customers here, so all we need to do is pop that 40 customers in right here and calculate the profit. So the profit in this case, or the predicted profit, is going to be 3.98. For the number of customers, we know that we have 40 showing up, and then we minus our 29.34. We actually calculate that, so 3.98 times that 40 minus 29.34, and we should get 129.86. So this right here, that is our predicted profit. So we would say we predict a profit of $129.86. So the whole idea of this is that there was no moment in our original data back up here where we had exactly 40 customers. But because we built this model and because we were convinced by the correlation coefficient that the two variables were related, we're saying that we're comfortable making a prediction of what would happen even when there's 40 customers. And all we do to make that prediction is just simply plug in that value and evaluate our model. In our next video, we'll be talking a little bit more about these predictions, specifically some of the limitations to these predictions and some of the things we need to be careful with. And we'll do another example running through building the LSR and then using and interpreting the results of that LSR.